Ciphers, ciphertext, and symmetric encryption play a crucial role in cybersecurity by ensuring the confidentiality and integrity of sensitive data during transmission and storage. For example, in a secure communication between a user and a server, symmetric encryption can be employed to encrypt the data, turning it into ciphertext, which can then only be decrypted by both parties using a shared secret key and then preventing unauthorized access to that information as a result. In this lab, we'll explore the concepts of the ROT13 cipher, ciphertext, and symmetric encryption using terminal commands. You will learn how to encrypt and decrypt data using the ROT13 cipher, as well as being able to utilize AES 128-bit encryption, similar to how the browser encrypts traffic after the initial session key exchange. Let's jump in. First, we need some plain text. So what we're going to do is create a variable called plain text, and then we're going to put some text inside of it. And we're going to say that this is a secret message. And a reminder that plain text is different than clear text. Clear text being that it has no intention to be encrypted, whereas plain text is the text before it's gone through its encryption algorithm. Okay, so let's go and echo the variable first, just so we can cleanly see the data in the variable. And then next we're going to use the TR tool, and this is the translate tool. And by using this, we're actually going to create a ROT13 cipher on the command line. The ROT13 cipher is a cipher that rotates the positions of characters, and in this case by 13 positions. So that ROT13 is a rotation of 13. And we can use the TR tool to translate characters up 13 positions very similarly, and then achieving the result of a ROT13 cipher. Okay, so let's see how this works. I'm going to echo the value of plain text, and then I'm going to pipe that into a TR command. And this is going to look a little funky at first. That's totally fine. It always does when you first see this type of command with TR. But let me try to explain it a little bit. The way that it works is that the first set of characters provided will specify start from A to Z. And then we need to provide a destination for those characters to go. And this is where the translation happens. The TR tool will then map and rotate each character by 13 positions if we suggest that the character should start from N to Z and then A to M. If that's a little confusing, just think of it like this. A would become N, B becomes O, C becomes P, and so on until Z becomes M. Finally, let's see our output. And there it is. We technically have encrypted output. And this is actually ciphertext now at this point. So why don't we just throw that inside of a variable? Let's instantiate a variable called ciphertext and put that whole statement inside. And we'll need to wrap all of that inside of command substitution so that it becomes fully evaluated whenever we call the variable. Cool. Let's echo the variable now, and just to make sure. Awesome. So there it is. There's our ciphertext. Now we need to move on to decryption. So in this case, let's make another variable, and we'll call this decrypted text. And all that we need to really do is reverse the translation there. So it'll look the same. Instead, this time we'll echo the ciphertext and pipe that into the TR tool, but we're going to do it in reverse. We'll start with the N to Z and then rotate that back into the normal alphabet. Okay, let's run it. Let's see what it looks like. And there it is. There's our secret message. So we've now taken a plain text message, we encrypted it with a ROT13 cipher by utilizing the TR tool, and then we decrypted it by reversing the encryption. And this is a very light form of encryption, mind you. We could say, though, that the encryption shared key is 13. So if we wanted to create a rotation cipher, a ROT cipher, and maybe not a ROT13 one, maybe we wanted to make a ROT20 or a ROT15, we could then say between two parties, if they were to say that the shared key is 15 or 20, and then they would be able to use that key to run it through a rotation cipher and understand one another. And that's pretty cool. That's technically symmetric encryption. The same key to lock or encrypt the text is the same key to unlock or decrypt the text. But let's use a proper cryptography toolkit, and for that we'll use the OpenSSL library. Inside of here, we can utilize a much more powerful form of encryption, and we'll use AES 128-bit, which means it requires a 128-bit key. And you've seen 32-bit IP addresses. You can see just how many combinations exist with that. When we get to 128-bit, we're talking about trillions upon trillions upon trillions to the nth degree of combinations. It's extremely difficult to reverse engineer at this point of time in our level of technology. It would basically be impossible at this point. Okay, so let's generate a key, and we'll run with the OpenSSL command with the RAND statement, and then mention that it needs to be in hex with 16 bytes for 128-bit. So that's technically our key at this point. Now what we want to do is we want to put that inside of a file. So we'll run that command again, but then we'll redirect it out to a key file. Perfect. And if we cat it, you can see it's a different key. It really shouldn't be the same, or we wouldn't have a good encryption suite right here. And just to be clear with a what is command on OpenSSL, it is essentially a command line tool to interact with the OpenSSL library, which contains a bunch of various cryptographic operations and functions like we're doing right now. And if we wanted to get a list of some of those functions, we could run the OpenSSL ENC for encryption, tax ciphers. We can see a full list of all the supported cipher suites. So quite a few. They all have their various different strengths. We're going to go with AES 128 ECB for electronic codebook. And this one isn't the greatest form of encryption, but it's easy enough to work with and it demonstrates the purpose. So what we want to do is go ahead and echo in some data so that we can work with it. And I've prepared a very special statement of data for us to work with that sort of enforces the concept over here. You can see just the number of possible combinations for a 128-bit key. So I'll put that inside of a plaintext.txt file for us to work with. Feel free for you, however, to use whatever text you would like. All right, now here comes the symmetric encryption statement, where I'm going to use the key we generated and encrypt the statement into a fully encrypted form of text. So we'll run the OpenSSL library again, run the ENC for encryption command, and then we'll specify the cipher suite that we'll work with. So AES 128 ECB, and then TAC capital K to specify the key, and we're going to cat out the contents of it. And then we need an in file, which is plaintext.txt, and then an out file, which is ciphertext.txt. Awesome. And that's literally how fast it worked. That's our fully encrypted form of text in a split second. And there's no way that we're reading that, and there's no way that we're cracking that, at least with today's technology. Okay, and what about the decryption portion? Same thing. Remember, this is symmetric encryption, the same shared key. So we go back in here, make some slight modifications to the command. So we'll add a TAC D after the NC portion, and that permits decryption. And all we need to do is make sure that we're specifying the in text is now the cipher text, right? It's different. And the out text would be the decrypted text. So let's just change that. And we're finished. Let's cat that decrypted text now. And just like that, we're back to the original text. That's pretty amazing, isn't it? So what you're seeing here, this symmetric encryption process, it uses the same key to encrypt and decrypt the data. This is what the client and server will use inside of a TLS session that's fully encrypted after they've completed the asymmetric encryption component of that process. And we'll see that in the next lab. That's how the initial exchange happens. But the key that they use to encrypt and decrypt data on both ends, it's this type of key. And we're talking about orders of magnitude faster. There's a reason for that. Symmetric encryption can generally be a fraction of the time that it takes for asymmetric encryption to perform the same process.